Everyone is talking about using AI to modernize legacy systems. I want to be direct about what AI actually does in that context. It doesn't solve the problem, it moves it. And because AI output looks thorough and structured, the problem becomes harder to see than it was before. That's not a criticism of AI. Actually, AI is genuinely powerful. Modern systems are better than anything we had 5 years ago. But power is not the same as access. And what limits AI on legacy systems isn't capability. It's what isn't there to be read. Let me be specific about where AI is genuinely useful. Code analysis, finding patterns, dead code, security vulnerabilities, refactoring candidates. Useful, legitimate. Dependency mapping, where the source is complete and readable. Generating documentation from existing well-structured code. Accelerating refactoring work, where the code base is consistent and the context is clear. All of that is real and valuable. None of that is what I'm talking about. So let's talk about the systems where the source isn't complete, consistent, or well-structured. Where the knowledge that makes the system work was never in the code at all. Legacy systems carry knowledge in forms AI cannot read. Not because anyone was negligent, because that knowledge never needed to be written down. The engineer who built it understood it. The team that maintained it understood it. The system ran, and that was enough. Design decisions made under constraints that no longer exist, workarounds that solve problems nobody documented. Behavior that was correct for hardware that's been replaced twice since. None of that is in the source code or accessible to AI. Now, modern AI systems are sophisticated. They can infer, they can reason about context, they can read between the lines in ways that would have seemed remarkable a few years ago. But there is a hard boundary they cannot cross. AI cannot read what was never written, and it cannot reliably make assumptions about external systems it has no information about. And here's the part that makes it worse. If the documentation about an external system is partial or outdated, which in legacy environments it almost always is, AI doesn't know that. It works with what it has. It produces confident output based on information that may be years out of date. That's not wrong input producing wrong output. That's incomplete input producing output that looks right. In embedded systems, this becomes structurally critical. The behavior of an embedded system isn't just in the software. It's in the interaction between software and hardware. The hardware abstraction layer, firmware running in external controllers, timing constraints that exist in the physical world and not in any config file, qualitative behavior that was tested and tuned empirically and never specified formally. An AI tool sees the software layer. It sees what was written down. It doesn't see the system. There is a second dimension that compounds this. Legacy modernization usually happens inside one system, but that system communicates with other systems. And the interaction across those system boundaries is often the least documented thing in the entire code base. Error codes, whose meaning was never formally specified, message timing that grew empirically over years, effects that certain signals produce in external systems that nobody ever wrote down because the person who built it simply knew. And in legacy environments, the documentation that does exist often describes interfaces to systems that were replaced years ago. The use cases have changed. The assumptions haven't. When multiple subsystems are gradually replaced over time, each replacement individually looks manageable. But the original calibration between them gets lost. No single document captures what changed or what the cascading effects were. This problem doesn't belong only to AI. A human engineer looking at the same code faces the same wall when the information isn't there. But here's where AI introduces a specific risk. When a human engineer encounters a gap, they typically recognize it as a gap. They flag it, they ask, they document the uncertainty. When AI encounters a gap at the system boundary, especially in edge cases, it may reconstruct plausibly, confidently, incorrect. And a confident wrong reconstruction looks exactly like a correct answer. No warning, no uncertainty signal. The gap becomes invisible and wrong. There's a concept in data processing. Garbage in, garbage out. Bad input produces bad output. The legacy problem is different. The input isn't garbage. It's incomplete. And incomplete input doesn't produce incomplete looking output. It produces confident output about a partial picture. AI tells you what it found. It doesn't tell you what it couldn't find. And it doesn't signal the difference. Think of it this way. If I have 5 balls in my pocket and I can identify 3 of them, that tells me nothing about the other 2. And if there are actually 9 balls, I don't know that either. AI analysis of a legacy system works the same way. What it returns looks complete. The gaps are invisible in the output. But there is a worse version. What if AI doesn't leave the gap empty, but fills it with something plausible, confident, coherent? Wrong. And you build on it. None of this means don't use AI. Use it where the data allows, where the code base is readable and complete, where the external dependencies are well documented, where the system knowledge exists in a form the tool can actually access. For everything else, the undocumented decisions, the hardware dependencies, the tribal knowledge that kept the system running for 15 years, you need to roll up your sleeves and go into the system first. That means reconstructing what was never written down and building the knowledge base that makes AI useful rather than confidently incomplete. AI can help once the invisible parts have been made visible, not before. Before you use AI on your legacy system, do you actually know what it doesn't know about your system?